Good, we've got here. Thank you to our tech team for sorting us out there. Welcome everyone to the Astronomical Society of Edinburgh. It was touch and go that we would get everything streaming, but we have, so thank you everyone for doing that. There we go. So you may have heard there's a certain Taylor in town tonight. Here he is, the real Professor Andy Taylor. So he is the one you all came to hear. I did ask Miss Swift if she would do a number, but she didn't respond to my emails, so I think she's probably a bit busy. This is what we've got coming tonight. Just a few slides from me, and then we hand over to Andy. A few news items coming soon. After that, it falls to me to do the Sky Notes for June this year, which is always a difficult month, June, because it's twilight all the time. Then after that, we'll turn off YouTube for our visitors. And we will have our AGM, which hopefully shouldn't take too long this year because there are no elections of people this year. Yeah, welcome wherever you are. We have members in the room here in Edinburgh, and we have members on Zoom from all over the world, and we hopefully have visitors on YouTube as well from where you are, so you're all very welcome. We haven't welcomed new members for a while, I don't believe. So these are the latest members from April and May. So Robert, Glow, Arlen, Errol, Kenneth, and Alison. Are any of you here tonight? I know some Alice is here. So welcome everyone. Welcome everyone to the society. We are around about the 200 mark, which is the highest in our history, which is great. So what we've got coming up over the next, the next 2 months really before our August break. On the 12th of June, on Wednesday, we have our usual Imaging and Observing Group meeting. That's on Zoom for members. That's been really popular and is going really well with lots of contributors to that, and we're learning a lot together with that. The 21st of June, Digital Skies for Ancient Contexts, using Python to investigate stellar data from Ramesside star clocks. I don't know what that means, but it sounds very fascinating. And that will be on Zoom for members only, and on YouTube for visitors. On the 5th of July, a hybrid meeting, so we'll be here again, and on Zoom and YouTube. Stellar Winds, the Givers and Takers of Life from Dr. Brad Gibson. And 12th of July, our usual Imaging and Observing Group meeting. And then the 19th of July, How to Design a Universe with Astronomer Royal for Scotland and one of our honorary presidents, Professor Catherine Hamans. And then after that, we will have a well-needed break after a very, very busy year. So that's what we've got coming up. The background I'm using is one of our latest images from our remote telescope in Spain. That's the Hercules cluster, is that right? Am I right in thinking that? I can't remember. And that one's from Mike Christie. And it's our deep field, really. It's not the Hubble deep field, but it's our deep field, and an amazing number of galaxies in there, and that's a labeled version of it. That is really all I've got to say. So, Andy, it's going to be over to you. We'll just swap over. Okay. That works. There's your.
Are we coming up?
Just give it a second. Yeah.
Okay, right. Thank you very much. I'll just check that I know how this is going to work. Okay, thanks, Mark, for introducing me, and thanks everyone for the invitation. It's great to be here. I did worry about people Googling Taylor and In Concert, so I apologize for anyone who's turned up thinking they're in the wrong place. But what I want to talk about today is exploring the dark universe. So I know that one of my colleagues, Alex Hall, was talking here recently, and he gave you a kind of introduction. So this is a spacecraft that we launched middle of last year, Euclid. And as I'll explain, its primary mission is to probe dark energy. So, because I know you've kind of been through some of this, I'll give a quick, brief reminder. But what I thought I'd try and do was discuss more of the science behind what this is trying to do and why, and then I'll show you some pretty pictures. So I'm hoping I get the balance right, and you can kind of enjoy the talk. Okay, so if we can, that's not. Down arrow. Ah, that's the animation I was after. Okay, so this is a picture of Euclid. This is a standard issue ESA person. And this was just amazing. I'll show you another image in a minute, but it's basically been built as Europe's dark energy satellite. There's a huge backstory, which I'm not going to talk about. At some other point, I'll maybe write a book about it. But there's been a dark energy war for the last 20 years between Europe and America. And we won. Okay, America has not got a dark energy satellite. It is trying to, but I'm very proud that, over the last 20 years, we thought about these concepts. I've been working with pen and paper, designing it. We designed kind of what it would do and worked out what science it would do, and I'm now leading a lot of the data analysis of this. But it was fantastic to actually see this done, okay? But it's interesting. It's designed to measure and to probe dark energy. I'll try and explain how it does that, but we'll get to this soon. It launched, as I said, the middle of last year. This is a still from the launch pad. Fortunately, I was not that close. We were about maybe half a mile away. And at the time, it just seemed like it was on the horizon. And we were kind of, it's a bit far. That's kind of, we'll not see anything. But it was amazing. When it takes off, it launched on a SpaceX Falcon 9 rocket. Euclid is actually in this little capsule up here. This didn't give it justice for the jet. The jet is like a blowtorch. It's the brightest thing in the sky you've ever seen. Okay, so it's not a long trail. It's just a powerful thruster pushing off. You can see we had perfect conditions, beautiful blue sky. And then when the sound hit us, it really just does go through you. Everyone says you get knocked off your feet by it, and you do. So I'm very glad we were nowhere near this, but it was very impressive. We were being looked after by NASA and SpaceX, and ESA had kind of shipped us across to see this, and they did an amazing job. It really was quite fantastic to watch and see it happen. This is a little bit more about Euclid. This is myself in the middle. This is Alex Hall, I said, who came and talked to you before. This is Arthur Luero, two of the people I work with. We got an opportunity to see this. This is in Cannes. I never knew ESA had a center in Cannes. I've been to Cannes. I've seen things, the movie stars there. But they have this huge facility which assembles satellites. So we got an opportunity to go and visit pre-launch, which again is quite unusual. You usually don't get an opportunity to go and see the satellite. So this is, so technically it's a 3-mirror Korsch telescope. It's got 3 mirrors in order to improve the image quality. The image quality for Euclid is paramount. It's one of the things we've worked really hard on. And again, I'll explain why. It's not just a competitor with Hubble Space Telescope. It wipes the floor with the Hubble Space Telescope. Okay, bold statement. I will show you. Okay, it's not got actually a larger mirror as that, but that's because we are doing surveys. We're covering large areas of sky, not again like JWST doing deep kind of field boreholes. Okay, there's 2 cameras, and I'll show you. It's about 4.7 meters high. It's 2 tons. It's €500 million. Euclid at the moment is costing about 1.2 billion euros. So I always say this is €500 million. We're about 0.7. Okay, fortunately, I don't get to see that. But what I mean there is the people who build it. The cost of that is where the other costs come from. So it's really kind of, even though we're focusing on the technology, and the technology is awesome. As I walked around it, I just felt this is just a solid block of technology and the most up-to-date that we've ever seen. So it was very impressive. But actually, an awful lot is the people who've come together to make sure this happens. Okay, on board we have 2 instruments. This is an optical camera. It was built in the UK, so we can be very proud. It's one of our major contributions to this. It's hard. I didn't put a person standing by this, but this focal plane, this is made up of little detectors like on your phone. Okay, but on your phone you probably have a little chip about that size. Okay, this is an array of chips about that size. Okay, so it's an awesome camera. It really is. I believe it's the largest scientific, I would say, again, not military, but scientific camera in space, optical camera in space. Okay, but again, we can be pretty proud because actually this whole thing is working beautifully. It's working brilliantly for us. As well as optical images, we've got a near-infrared and a spectroscopic camera. This is built in Italy. So again, this again, equal kind of price tag, but again, all this is working as well as we'd hoped. So it's doing kind of colors. So as well as kind of exquisite images, we also get color information in order that we can judge the types of galaxies, the type of stars in there, but also their distances, which again is very important to what we're trying to do. Okay, so Euclid launched, it was actually on the 1st of July last year. It journeyed then out about 1.5 million kilometers, and it's out here. It's just beyond the Earth-Moon system. Okay, we orbit about once a year around here because we got the mass from the sun. Euclid orbits once a year in kind of step with us because it's got the mass of the sun plus the mass of the Earth and the Moon. So its orbit can be a bit further out, but it stays kind of in sync with us. Okay, it took about a month to get there. In that time, we were shaking down how things were working, getting first images. A very exciting time because, you know, having launched this thing, you've just rattled it to death and you're kind of thinking, is it going to work? You know, even just switching it on, everything can go wrong. And actually, you know, it's like booting up your computer. It was in sleep mode, and we just said, wake, and it went bing. And then I'd say within a few days, maybe about 10 days, we saw the first images. And the first images were awesome. Okay, so that's kind of where we were. Okay, Euclid's mission. So ESA likes the idea of having a mission statement. We're built for something, not just to kind of go and observe nice things, but that, again, is something we'll do, but to propose what is the scientific purpose of this telescope, and then design everything for that purpose. Okay, so Euclid, I just clicked the wrong way. Let me go back. Euclid has sort of these 4 mission statements. The primary one is the measuring the property of dark energy. Okay, again, I'll come back and explain that. But this being primary actually turns out to be very useful. And a lot of kind of people involved in building projects or doing something for some reason, you've usually got compromises. There's usually something you want to do or something else you want to do, and then you have to sit down and go, well, we can't both do it, so, you know, we'll compromise on what goes where or what is efficient. We never had to do that with Euclid, because there was only one question we had to ask, was would it improve or make it worse to measure dark energy? And if it improved, we did it. And if it made it worse, we did not do it. That made us very unpopular with lots of people who would like a telescope like this to do other things. But actually, the specifications for Euclid are so high, we're actually fantastic for almost anything and everything that people want to do. Okay, but this meant that we have a mission, is to measure the properties of dark energy in a way never done before. Okay. Also, probe dark matter. Again, I'll talk about how to do this, measure the mass of neutrinos we think fill the universe. Test Einstein's theory of gravity on the larger scales. Okay, we pretty much feel we understand gravity locally, even in the solar system. But as we get to larger and larger scales, we see sort of odder and odder things. And we just kind of think, okay, have we got gravity right? Maybe there's a reason we're not seeing things we expect. And Euclid's aim is to try and test some of those on the very largest scales of the universe itself, or the observable universe. Also, the power of Euclid is in what it will do, it's aimed to try and look and probe back into the early universe. Okay, so hopefully look at kind of footprints there to probe the very earliest moments of the universe. Okay, I'm not going to talk very much about these 3 down here, but I'm going to focus on the issue of dark energy and try and explain why is that our primary mission statement? Why is that the thing we're really going after? And the reason is that what we find is over the last 20-odd years, maybe even 30 years, we've growing evidence to find that the expansion of the universe is not what we expected. We thought in fact, we have what turns out to be a very detailed and accurate model of the universe. Surprisingly, you might imagine as you get to larger and larger scales, things get more chaotic and we'd have no way of really understanding what's going on. It doesn't seem to work like that. It seems we get to larger and larger scales, actually things become simpler. To the point where even our simple mathematical models, okay, actually seem to fit the data we get from the universe very well. But as I'll show, it all started to point in one direction, which was that the universe was seeming to accelerate in its expansion. Okay, now, why do I say that? So let's look at some of the evidence, or at least some of the indicators, the probes that are telling us about this accelerated expansion of the universe. So this is a picture of the cosmic microwave background. This is another European satellite, the Planck satellite. It mapped, really this is a microwave picture of the sky. Okay, there is a galactic plane here, it's been removed. This is showing variations, but this is basically an image taking us back to the first few 100,000 years in the lifetime of the universe. So we're looking back nearly 13 billion years. And it's a point where the universe, if it's expanding, you go backwards in time, it contracts, it heats up. At some point, it gets as hot as the sun. Okay, we know the sun is a big ball of plasma, and that's how the universe was. It was full with matter and radiation. It was interacting a lot, but it was really a ball of plasma at the time. But we also know the sun has a boundary. At some point, light can escape from it, things become cool, the plasma is contained, and photons eventually leap out and we can see them. Sort of a similar thing happened here with the universe. The universe cooled and that plasma broke down, and all of a sudden the radiation could travel unhindered by the plasma. And it traveled across the universe, and eventually it hits something. It hits our telescopes, and we can see an image. We can look back that 13 billion years, and we can see a map of what the universe looked like. So at the time, this was everywhere. But of course, as things cooled, because we're looking back in time, every direction we look is going back in time, and until that point, we see that plasma. And it's not uniform. It's pretty uniform, but we see there are slight variations here. What we believe is that's the structure in the universe. Okay, it's a structure in the universe at the very early times. It's slight changes in the density of the plasma, slight changes in density of the matter, including things like dark matter. Okay, we didn't believe that. So these are real features. Okay, it's not noise. This is a real feature. Okay, and it's really there. I mean, I've run a CMB experiment. We built one and shipped it down to the South Pole and switched it on. And after about several hours, we had a tiny little map. Right, so you can actually see it. If you had your microwave polarization glasses on, you could look up and you would see this sky there. Okay, so it's really there. But we can take maps like this, we can analyze them, and we can try and compare them with our theoretical picture of what we think the universe looks like or what it contains. Okay, so we can try and model this. The way we do it is basically try and break things down in terms of information. This is what we call a power spectrum. Essentially, we can just think of it as being those temperature fluctuations, in this case squared. This is angular scale. Because we're astronomers and physicists, we do everything back to front. So large scales down here, small scales down here. Okay, for technical people, we've done a spherical harmonic decomposition in multipoles. The multipoles are here. But the angular scales are really interesting. But you can see it's not uniform. As we've broken down that pattern onto different scales, it's not just that it's noisy or it varies. It varies in a very specific way. Okay, out here, really what's happening is that photons are getting dragged as they climb out of the potential wells of dark matter. Okay? There are oscillations. The oscillations are coming from the oscillations in the plasma. It's sound waves in the plasma. Okay? And our theory is good enough that it's able to predict these things. And so the green line here is the theoretical prediction. Now, a lot of the theoretical work in this goes back to the 1960s, well before any of the spacecraft we're talking about, well before even the detection of the microwave background. Okay, and what's happened is basically the theory's got better and better, so we have better and better predictions. So at the point when things like Planck switched on, we could do a comparison of the data against our theories. Again, remember, we didn't just have one theory. We've got lots of theories. And even with one theory, you can vary the parameters in the model, change things to see if it fits better or worse. And so what's plotted here is the best fit model we have against the data. You can see the error bars are tiny, but you can see it doesn't matter. The data is following everything almost perfectly. There are 6 numbers in this theory, and yet we get all of this detail. This is one of the best matches in physics compared to data, compared to a theory. Okay, so we're very proud of it in cosmology. We have something that looks so good. So that's good. That's the positive side. We understand the physics very well. We can make predictions like this, and then we can compare them with the data, and lo and behold, we get something which matches very well. What was strange is, as I said, there are various kind of knobs we can change on the theory. We can increase an element here, we can take away something there, and we can try and see what better agrees with the data. When we do that, this is what we get. Okay, it's barely the components that go into that model. Okay, so maybe not surprisingly, there's a small amount of radiation around today, so we can measure that again in the microwave background. There's known matter, the stuff that makes up you and me. Okay, it's all kind of similar stuff. That's good, it's accounted for. We can measure how much is there. But already you can see there's a whopping great amount of dark matter, right? We put into our theories stuff that seems to explain rotation curves of galaxies or galaxy clusters. We put that into our models to try and explain the microwave background. It does fit. It fits perfectly. But it says that 25% of everything must be dark matter. And you can see that's a factor of 5 greater than everything we already know about. So, of course, that's already a concern because we want to know, well, what is that, right? It's kind of in our models, but as a simple thing. What's even worrying is this thing. There's a huge component of something else we call dark energy, okay, which doesn't seem to react like anything. I'll try and explain why we have this in, but it seems to dominate, and we can't do without it. If we remove this element, we get no fits, nothing fits, no model. Nothing we have will come any close to fit. So it gives us a conundrum that we have something which works very well, but it's got some exotic components. We'd like to understand what these are and where they come from. And I'll just notice that, again, we've got Einstein gravity in there. We have assumptions about initial conditions in there as well. Okay, so that was one indicator. Just from the microwave background itself is so good that it tells us that there are these components, and we don't really understand these components. We also get things from the patterns of galaxies. So this is from, actually, this year, the Dark Energy Spectroscopic Survey, DESI. And hopefully you can see here, we're at the center here looking out, and this is giving us positions of galaxies out in the universe, okay? This is roughly getting across, halfway across the universe in both directions. It looks pretty uniform, which is good, but if you zoom in, then you can see there's actually structure here. There's this sort of cellular structure, which we call the cosmic web. Okay, and it's clearly a pattern, right? There's a pattern going on there, and we want to know what's laying down that pattern. Now, we think we understand. We think what it is it's just random variations. We saw that in the Kobe maps. There were random variations in the density. If we start with that, and then we let gravity work its magic, gravity pulls things together. It opens up large voids or empty. It pulls gravity together, it brings things together. And generically, it seems to produce structure like this. Okay, but it depends on the type of dark matter. So that gives us an opportunity here. We can try and compare these patterns with what we would predict or measure from our theories of cold dark matter. And in more detail, it'll actually depend on whether there's anything this dark energy component that we've put in. It'll depend on those. So what we do is we run simulations. This is a simulation that's run with cold dark matter. And just spontaneously, this cosmic web structure appears when we run these simulations. Okay, we don't put any magic in, we don't mess around. We just basically put in random variations of the density field and then turn on gravity. And gravity just spontaneously produces these. Okay, and the nice thing is that that's all you seem to need to have in order to produce or replicate these sort of patterns in the distribution of galaxies. But it needs dark matter. If you throw away the dark matter, it doesn't look like this. It doesn't look properly. Or if you change the type of dark matter, I've called this cold dark matter because that means there's no kind of thermal velocities. But if we change the thermal properties of the dark matter, it erases all this structure. So we know pretty well that it must be something like this, even if we don't know in detail what it is that is producing this. Okay, so there's sort of nice pattern recognition here, that we're using the patterns in the structure of the distribution of the galaxies to try and understand what's going on. It's telling us something about dark matter, and in detail, it will tell something about the dark energy as well that we seem to be seeing. Again, in terms of trying to measure information from the universe, again, maybe it's a bit frustrating. You're looking at galaxies, okay, galaxies, stars. How do we know the stars actually form matter? Our theories predict where the matter is. Okay, what's the link? It could be all sorts of complicated things going on. But actually, we have a nice technique called gravitational lensing, which allows us to look directly at the matter in the universe. Okay, and this is one of the areas of speciality. Both galaxy distributions and gravitational lensing are one of the specialities we do at Edinburgh. So this is a gravitational lens, so hopefully you can see this. There's clearly a group of galaxies here. These are the large blobs, are the main objects in that group of galaxies. But hopefully you can see in the background, there are sort of some heavily distorted images of galaxies as well. And also up here, okay? It's a bit like if you took kind of a wine glass or a glass ball and put it in front of some images, you would see heavy distortions. And that kind of analogy is actually very good for gravitational lensing. It's very much like optical distortions and optical lensing. And just as you might imagine that if I put a large ball here, it might produce these distortions, similarly, you could imagine in your head, there must be a large something which is causing these distortions. Now, Einstein told us that the mass of objects would bend space-time, and that could lead to these sort of distortion effects. So the predictions have been there for a long time. But it's really gratifying to see that actually in the data you can see them by eye. The size of this roughly tells you how much mass must be in there. Okay? Now, if all the mass was actually just in the stars you can see, those distortions would all hug around these objects. So the fact that by eye you're seeing something around here tells you there's a structure which is that big, but you can't see it. That's the dark matter. Okay, and when we add up the amount of dark matter inferred by this, it's way bigger than we would find in stars or galaxies or anything else that we call normal matter. It would agree with the numbers we saw from the cosmic microwave background. It's about a factor of 5 more than you'd see. So we now have kind of other evidence just locally where we see this going on, and it's everywhere. It's everywhere we look. One of the nice things we can do is not just kind of infer how much mass is in here. We can actually use these distortions and tiny distortions in these other faint galaxies in order to construct a map, make an image of where the dark matter is. So here, in sort of the blue and purple scale, is where we've reconstructed where the dark matter is. Okay, so it's concentrated around the main galaxies in this group, of this cluster, as you might expect, and then it dies away as you go further away. So we're not putting in a model in here. We're not making any assumptions. We're just saying, let's believe that gravitational lensing is caused by gravity, as Einstein told us. And we'll use that just to try and reconstruct the mass we need in order to see those distortions, and that's what we get. So it really is making an image, okay, of what's going on with the dark matter. What we would like to do is sort of extend this from around clusters to look on these larger scales, just as we've done with the galaxy surveys. So this would be our prediction. Okay, so we're saying, okay, if we really believe in this idea of cold dark matter as being the right answer, our simulations predict that if we could see that dark matter, it would actually look like this in detail. So I love this because it's so complex. Okay, in some ways it's very simple, but it's clearly a network. Again, it's a cosmic web. It's a cellular structure. There are holes have opened up where gravity has pulled out the dark matter. And it's formed also what we call filaments. So these are where kind of gravity is pulling things together into a line. Okay, and between the filaments, you can see that these groups where gravity is now drained matter from the filaments to form these groups, these nodes or clusters. Okay, so if we had our dark matter glasses on and we looked around us, this is what we would expect to see. Okay, so, well, observationally, where are we? This is nice to have in a computer. It's nice, to show things like this. But what we really want to know is that really out there or not? Well, this is where we currently are. Okay, it's a little blurrier. Okay, at least the color's right. That's always good. But you can see there are similarities. Okay, you can clearly see that there are groups here. There are nodes, as we saw in the dark matter maps from the simulations. There's maybe even starting to be some evidence. There's certainly images that there are holes in here where there are the voids. And there's maybe some indication there is sort of filamentary structure coming on. Okay, it's clearly not great at the moment. It's pretty crude, but at least it's not completely different from what the simulations would predict. What we really want to do is now go on and basically improve these, get high resolution. So I want to get an image that looks like the one we just showed from the simulations. Okay, so by eye, you could go either, yeah, actually this looks pretty much like the simulations are predicting, or you could go, ooh, no, hold on, there's a big discrepancy. Okay, so something is different from what I was assuming is happening. Okay, and I think we're getting there, and certainly what I'll try and explain is just how powerful we're going to be in a few years in order to do that comparison. Okay, so we've got various indicators, certainly that dark matter is there. It looks like the kind of dark matter we think it is. We've got both galaxy surveys, lensing, and actually the cosmic microwave background. When we try and fit our models to the statistical properties of here, we get an agreement in the modeling. All the models give us the same answer, that there's something there with Dark matter, 5 times normal matter, plus this huge amount of what we call dark energy. Okay, so we're getting consistency, but we're still confused. We're about that stage probably in the late 90s. But on the basis of that model, there could be a prediction. The prediction was that this dark energy, again, discuss what it is, should be causing acceleration of the expansion of the universe. And that was the big question, was given it was predicted that, could we show that? And in the late 90s, then a couple of teams decided to test that. And so they looked at these supernovae. This is a supernova going off near a large spiral galaxy. What's nice is its brightness is nearly as bright as the whole galaxy itself. So you can see these things all the way across the universe. Okay, and they form what we call standard candles. It's slightly more complicated, but it's a bit like having your light bulb. You know what the wattage is. Okay, you could take another light bulb. It's got the same wattage. You move it further away, and because the light goes down as inverse squared, if you saw it dimming, you could guess how far away it was based on the fact you know how far the nearer light bulb is. We do the same thing here. So we can get both the distance here, and given we can get the distance or the amount of expansion that's happened in the universe from the neighboring galaxy, we can work out what the expansion history of the universe is. These things themselves, I said, type 2 supernova. So these are coming from companions to objects which are becoming gas giants. So these are things that have had their life cycle. They're stars that have been, come and gone, blown up and then collapsed down to become white dwarfs. But if they got a partner, a binary with them, eventually these become supergiants, blow up, and if they're close enough, they'll start to pull material over here. And essentially the mechanism is that these will get larger and larger until they hit a critical mass and temperature, and then they go bang, and that gives us our supernova that we can try and calibrate. But I say we can get the distance from this, from the brightness. We can get how far in terms of the expansion history of the universe the galaxy is, and we can make plots like this. This essentially is different models of our universe showing the expansion history. So this is roughly the size of the universe. And then we've got kind of billions of years look-back time from today. Okay, so in some of these models, and in fact the models we used to think were the correct ones, we expected there must have been a big bang, there's an expansion at some point in the future, all that dark matter would pull things back together and we'd have a big crunch. So these models for a long time were the favored ones, at least theoretically. There are even ones here where there's expansion and then it reaches a critical stage where it just coasts, just keeps on going. And there's one here which is just what we call a coasting. It's linear expansion. Okay, but in here there's one where we've got dark energy, and it starts off looking a little bit like this model. It's slowing down, but then it starts accelerating as dark energy kicks in. This is the data. Okay, so you can see it's clearly not agreeing with this. Okay, maybe you could argue that it's maybe close to the coasting model, but it looks certainly more like the acceleration model. So this was the clincher. We had lots of evidence coming from the microwave background. We had lots of evidence coming from galaxies and gravitational lensing. But this actually was looking at the expansion history of the universe and seeing that it's not turning over. It looks like we're actually starting to accelerate. This was such an important detection and confirmation. And it was around 1998. Then this is the cover of Science from December. Is that 98 as well? Okay, just saying this discovery the universe is accelerating, okay, is a major discovery. The reason is that, again, we think the universe operates through gravity, okay, and we kind of do understand gravity at some level. You know, those plots I showed you of the expansion history, even as though the universe sounds grand. But actually, a lot of these, what we call trajectories, expansion and contraction, is very much like, what you'd expect on the Earth if you have an apple. Okay, you throw it up, it expands up, and then it comes back down again. You can imagine if you threw it hard enough, it might leave the Earth and just keep on going forever if the universe was empty. So actually, the physics behind this is an awful lot like your intuition about what happens with gravity. What you do not expect is to throw your apple up, it slows down a bit, and then accelerates off forever. You would think something very mysterious is going on. That's what we're seeing. That's the level of confusion, is why all of a sudden has the universe, if it's working under gravity, decided to start accelerating. Okay, and that discovery then is led to the to a Nobel Prize in 2011 because it was seen as being so profound. Okay, so we live in an accelerating universe, but what's causing this acceleration? Well, one of the reasons we have a model, and one of the reasons we had a model just to compare to, was that this chap here had introduced it many years ago. In his theory of gravity, Einstein, around 1917, introduced what he called his cosmological constant. Okay, so I'm hoping maybe some of you can remember back to physics at school, but the force of gravity is given by minus Newton's constant times the mass divided by r squared is r. And it's true even in Einstein's theory of gravity in weak field limits, it becomes right, okay? So if you have a mass here, you expect forces towards it. When Einstein was working on his theory of gravity, he realized there was extra freedom in his. And perfectly legitimately, he started to explore that extra freedom. And that freedom basically translates as to putting in another part of gravity which no one was aware of, which was to have a term like this. So lambda is his cosmological constant, it's just another constant within the theory, but it increases with distance, so it gives a repulsive force. Okay, at the time, Einstein was trying to build models of the whole universe, right, 1917. And at that time, he didn't really follow what was going on in any discussion, so he thought the universe was static, a reasonable assumption at the time. And what he tried to do was make a universe where these forces balanced, and so he had a static universe. Of course, in the 1920s, Slipher and Hubble and others showed that the universe was expanding. And of course, he actually kicked himself because he realized he could have predicted that. If he hadn't been so hung up on that the universe must be static, if he hadn't had that term, he would have just sort of said, well, hold on, there's this instability in gravity. Either it's got to be collapsing or expanding, so I would predict it was either of those. But on the other hand, he'd done nothing wrong by introducing this. His theory of gravity does predict there are extra forces in there. We just usually aren't aware of them. So this term hung around. It was in textbooks. Actually, it was dropped from textbooks, but it was in people's papers. And every now and again, people would sort of spot some anomaly in their data or something that looked a bit weird, and often they would say, I wonder if there's a cosmological constant. Oh, well, and move on. Okay, but people were talking about, and it was always there in the models of things to explore and to test. In addition, in quantum mechanics, interesting things were happening. Werner Heisenberg in the 1920s, in his calculation about how quantum mechanics might work, found that there must be an energy associated with the vacuum itself. There was a term in there which he couldn't explain initially, but then realized that it must be to do with when there's nothing, when everything's at rest, there's still energy about. Okay, so his kind of prediction of that, if I can start this, is at its lowest energy, okay, classically it's static. Classically you just think if there's something got no energy, it's just going to sit there. Well, Heisenberg showed that quantum mechanically that can't be true. Quantum mechanically, things cannot just be at rest. They must still be moving around. They still have energy, okay? And that this energy increases as you go to smaller and smaller scales. But it seemed odd. It wasn't clear what this meant. You know, how can things just have energy? How can they just be sitting there? If it's at a minimum energy, why is it still moving? Really, this wasn't fully explained until Paul Dirac in the 1930s came along with his theories and described how particles and antiparticles in vacuums would appear. So his idea was that in the vacuum has sort of an energy. And we can borrow energy for a short time scale. It can make particles and it can destroy them. So you can get particle-antiparticles creation and then being destroyed. So this really was saying there's an uncertainty principle associated with the vacuum. Vacuum energy, empty space is not empty, really. It's got an energy. And that's a fundamental prediction of quantum mechanics, that there's something going on there. Okay, we may say, yeah, but this is all quantum mechanics. It's fantasy, right? It doesn't mean anything in the real world. It's not true. Okay, unfortunately, when we make calculations in quantum mechanics, and remember, our world runs on quantum mechanics now. My computer runs through quantum mechanical processes, right? The internet works through it. When we do calculations, we find that there are terms that require, which require vacuum energy terms, such as Heisenberg found and Dirac could explain, are required in the calculation. If you take them out, the calculation gets it wrong. If you leave them in, then you can understand how a laser works. or how fluorescent lights work. Or even, this is a nice one, this is just a bit of block of material splitting the beam of light in two directions. The full quantum mechanical explanation for that requires a vacuum energy in there. Okay. We also see it's measured in the lab. There are various effects. There's a thing called Lamb shift in the frequency of light, and Casimir effect. In the 1940s, these were being measured in the lab, and they were fully explained by including vacuum energy terms. So quantum mechanics is very clear on this. It says, yes, there is energy in the vacuum. Okay, so we need to keep that in mind. The problem is that most of the time we don't have to worry about it. Certainly in the lab, you just measure, differences made by the vacuum. The problem for us, certainly in cosmology, is when we turn to Einstein's theory of gravity. Okay, we all know that mass bends space-time, but that bending of space-time and gravity depends on a total energy. We can't just pick and choose which things we're going to add to cause this curvature of space-time and cause gravity. Okay, it's the total energy. And that means we have to add together, if we include Einstein's cosmological constant, that's got to be in there. And if there's vacuum energy, and we've said we've been measuring vacuum energy for decades, the vacuum energy has to be in there to add to the total energy. Okay, so there's energy in the vacuum. Maybe that's not so bad. Can we estimate how much energy is in vacuum? Well, let's take those two terms separately. Let's take Einstein's cosmological constant. At the moment, it's just a constant. It's another constant in nature. It's like Newton's gravitational constant, okay? So we have a choice here about what to do with it. We could say, okay, we've got a new constant in gravity. I wonder if it's related to Newton's constant, which is the other constant of gravity. I don't have to do anything sophisticated. I could just say, okay, dimensionally, I've got to say how they're equal. I'll just say, dimensionally, lambda has to be going roughly as 1 over Newton's constant squared, and that gives me an estimate of what maybe lambda might be. Okay? The problem is that this is much greater than anything we observe, than the values being measured in our observations. So again, we could take another stance and just say, okay, that idea was wrong. Okay, just forget that. It's just maybe a new constant of nature. It's like Newton's constant. Can't predict it. Okay? Okay, that's maybe one way of dealing it. Fine, we can measure it from our cosmological observations, and then we just write it down, and that's it. Job done, go home. Okay, but there's a problem. There's still got the vacuum energy coming from quantum mechanics, and that can be calculated. Quantum mechanics gives us a way of estimating how big this should be. Okay, so we do that. The value can be calculated. And what quantum mechanics says that, say we take a box of side L, the energy associated with the vacuum is given, this is Planck's constant, and this is the speed of light divided by that length. Okay, that's the calculation we would end up if we were trying to work out the energy that's in the vacuum. But you can see what happens. As we shrink the box, L, the amount of energy that we're inferring in the vacuum goes up and up and up. If we say L goes to 0, this goes to infinity. Okay, but that can't be right. Okay, must be doing something wrong there. Maybe we should take some scale. Okay, so I've put here the Large Hadron Collider. Maybe put it the energy of the Large Hadron Collider. It's got to be bigger than any scale or any energy we're used to. So let's put it large, out of harm's way. Okay, Large Hadron Collider, or the thing here, the Planck scale, which is even bigger when gravity and quantum mechanics kind of blend together. Okay, but it gives us maybe a way then of estimating what this energy in the vacuum is. The problem is that either way, with lambda and vacuum energy, our prediction is 10 with 120 zeros after it, orders of magnitude larger than observed. This must be the ultimate doh moment. Okay, and actually this has been well known. I mean, these calculations, even the rudimentary versions of these calculations go back to the 1920s. Okay, Enrico Fermi was writing stuff down and going, there's a problem here, and everyone's going, it's all right, don't worry about it, it'll go away. And in a sense, over the next kind of 100 years, it's just come back to bite us. Okay, where now we're seeing effects of this in our data, but we don't really have a good understanding of why it's there. Okay, let's go and conceptualize this a bit more. Okay, so how much larger is that, 10 to the 120? Okay, so here is my simple kind of way of trying to fathom that. So if we measure the energy of the molecules in this church, okay, the energy associated just with their movement is roughly about the energy of the cosmic of the we see in dark energy from our observations. Okay? But the prediction says that all of the energy everywhere in the observable universe should be in this room. Okay, that's the discrepancy. Okay, I don't know about you, but I have not noticed that. Okay, so what do we do? How do we interpret this? Well, there's also, I guess, another way of looking at it. We could put it another way and say, okay, what do we get wrong in our calculations? Where do we go wrong? Is there a way of just correcting that to try and get some sort of agreement? Well, let's go back to our calculation in a box of how much vacuum energy there is. So what scale would this length have to be in order our calculations match the observations? Okay, and the answer is 1 millimeter. Now, that's really weird, because normally when we're talking about fundamental physics, we're kind of, into very small scales and subatomic and whatever. Okay. This is then saying that in order to match that calculation to observations, we need to be changing the physics of the vacuum around us, and it has to happen on the scale of 1 millimeter. Again, I don't know about you, but I thought we understood physics at the scale of 1 millimeter. But it's saying, either it's saying no, or it's saying something is profoundly wrong with these calculations, but these calculations are the one which gives us observational agreement in the laboratory. So where did we go wrong? It's not clear. So what protects us? If there's this violent quantum vacuum around us, is it there? What's protecting us from it? What's going on? And the blunt answer is, we don't know, right? In physics, we don't know how to explain this. We don't know what the right direction is to even explain this. It's a very difficult problem. To give you an idea of how difficult it is, it really pushes our imagination to try and explain it, because we've said we need to fix physics really at the scale of 1 millimeter, but in doing that, we don't want to change any of the other really extraordinary accurate predictions we make. So how do you do that? I think we just don't know. To give you an idea again of what is postulated, I hope this is gonna, yeah, there we go, okay. So extra dimensions, okay, maybe I can sweep it under the carpet. Maybe the universe has extra dimensions and I can put that 10 to the 120 vacuum energy, that violent vacuum energy, I can push it out of the way and it will seep into an extra dimension and we don't have to worry about it. Does anyone know what this thing is? Well, it's a tesseract, yeah, hypercube, yeah. So it's a 4-dimensional object projected in 3 dimensions. Okay, but it's using that kind of concept. There's an extra dimension out there. But it's that level of kind of almost desperation we have in trying to explain what's going on that we're saying there's got to be something fundamentally different. And these extra dimensions must be on the scale of around 1 millimeter. Okay, but somehow we don't see them. Multiverses. Okay, again, maybe the calculation is correct, but maybe it varies in different universes. And then we just happen to live in a universe where it's quiet, so we don't get blown apart. Maybe, but we don't really have a theory of a multiverse. They kind of come out of string theory, but we don't really have a theory that makes predictions that we can test. Okay, but again, it's just pushing us. It's how we're pushed to the extremes in trying to explain what's going on. Holographic universe, I like this one. Everything we see is a hologram. Again, this comes from, again, string theory. And it predicts that essentially, even though we think the universe is 3-dimensional, really our reality is 2-dimensional. Okay, we can be projected onto a 2-dimensional, the whole of the universe can be projected onto a 2-dimensional surface, and we get exactly the same physics as we experience. Okay, like crazy, but there is a theorem within or evidence within string theory, not that our universe is like that, but in their version of universes like that. In the holographic universe, then there may be ways of trying to accommodate this. Okay, slightly less prosaic, then maybe there's another way of doing this by eating the vacuum energy. Okay, so this is my Pac-Man, which is, so you can do this, or in principle you can do this. A new field or a particle like the Higgs field could cancel the vacuum energy. Okay, so I've got my field eating vacuum energy there, and then it can cause the universe to accelerate. This is an area, of course, that has been explored. In a sense, for a physicist, it seems like an obvious route. But Steven Weinberg, Nobel laureate, many years ago showed this is very hard to do, right? So it seems like a promising thing, but actually technically it's very hard to do. However, in the last sort of year or so, work by myself and my team found a way to do it. We think we have a way we can actually solve the problems that Weinberg raised, and we may have a way we can have a field eating the vacuum energy, and it would save us from this vacuum catastrophe. So, but again, it needs to be tested. Nice thing about it is it's simple enough theory. A lot of these theories will make predictions about what the universe should look like, and we can go about and then test them. Okay. In some cases, they may be right. Hopefully, in some cases, we get them wrong, and we can move on to new theories. Okay, but it's worth thinking about this dark energy, this stuff that's causing the universe to accelerate, because without it, our universe would have done this sort of trajectory where it would carry on. It might have carried on, or it may have gone into a crunch. It's radically changing the fate of our universe from something we thought we understood to something where it's just going to keep on accelerating. So really, we do want to try and probe into it, not only just so we can understand the physics, but so we know what's going to happen in the future. The way we can do it is going back to the probes I discussed at the start. Okay, if we have these extra forces, if in these theories I'm proposing might seem fanciful, okay, and we actually have hundreds, we probably have thousands now of theories that try and explain this. All of them will leave, to some extent, fingerprints in the distributions of dark matter over here from gravitational lensing and from the galaxy distribution. Tiny distortions, tiny effects appear depending on what our theory of dark energy is. So in order to test them, what we really need is something that maps these galaxies and dark matter across the universe to very high accuracy, so we can try and test our theories the way I showed you with the cosmic microwave background. And that's what Euclid is actually doing now. Okay, so Euclid down here, it's trying to make a map of the sky, just filling in here where Euclid's sky will be filled. So over the years, it's going to build up till we're trying to look at the extragalactic sky. So we're avoiding this, which is the galactic plane, because we can't get confused by all the stars. We're actually avoiding this. This is the ecliptic plane, the plane of the sun and the solar system. And it's because there is gas there. And we are so sensitive, even the gas in the ecliptic plane will confuse our measurements. So we avoid it. So we're going to build up a map of the extragalactic sky in order that we can look out into the universe, and we'll make maps of where the galaxies are and where the dark matter is using gravitational lensing. Again, to do this, we'll measure images of about 1.5 billion galaxies. Okay, that will come from the visible camera I showed you. And we'll measure colors both from the near-infrared instrument, but we'll also use colors from the ground in order that we can get distances for the galaxies. So we can make basically three-dimensional maps of where the galaxies and the dark matter is in the universe. On top of that, we'll have about 35 million galaxies with spectroscopic one is very high-resolution images that tell you, or very high-resolution spectral images that tell you more detail the distance to galaxies. But this is intriguing because by proposing this, you'll basically get a map of the universe, right? You're going to see almost everything in it for the first time, which is clearly just a huge resource for all of astronomy, for all of us. Okay, this will all be made public, so everyone can go and look at the data and see what's in there. What I think is interesting is that I'll show you some of the recent images we got, but no human being will look in detail at all of the Euclid data. It's now going to be too big. That means there are always going to be new discoveries that people will look at a patch of sky no one else has looked at and go, oh, that's interesting. Hopefully it's not the mothership, right? But it's going to be something interesting or something new, and we'll work with that and use that for many years. I think Alex probably showed some of these images in his talk. I'll show you them again just because I love them, but I'll also show the new images that came out a few weeks ago. So again, this is just comparing, this is a stellar globular cluster, okay, and what I wanted to show here was the comparison with the Hubble Space Telescope. Okay, same resolution, same depth, but it would take you hundreds of scans of the Hubble to get this. This was done by Euclid. Well, actually it takes about an hour to do all of the observations. For the optical part, this takes about 15 minutes. It'll look at this for 15 minutes, and then it'll move on. It'll never go back. Okay, but it gets that kind of resolution. And even with this, the people working on these objects, they've always had to have patchworks. And they're now going, hey, the whole object is in my field of view. This is great. I can now study the whole thing. This is the Perseus cluster, so objects down here. And again, what people are interested in is that the stars around here are extending out into these halos. well, these halos are dark matter halos, so somehow the stars are being trapped in the dark matter halos. We didn't know that before, didn't know in detail, but we're now able to see it. For a bit of fun, I thought I'd show you the ground versus Euclid. So I showed you the Hubble in comparison. This is an image from the Sloan Digital Sky Survey of the same patch, and then we switch on Euclid. And then, hopefully, yeah, there we go. As I said, you can see that all these stellar halos extend further out. Oops, let's go back. All these stellar halos go further out, further than we expected. But also the density of stars in the background, the density of galaxies in the background, these are all galaxies, it goes up hugely. These are all what we're going to use for gravitational lensing. So, you know, these things will have an immense data source. This is a hidden spiral galaxy. It just demonstrates our infrared capabilities because this is hidden behind the galactic plane. Normally can't see it, it's hidden by gas. We can see it very clearly. A regular galaxy, again, you can see this star formation events going on all over the place in this, which again would be hard to do even with Hubble to cover this area and see all these things. This I love. This is the Horsehead Nebula. Okay, again, Hubble would do a little patch there and have to do a patchwork to do this. And suddenly we've got a whole image of this thing. So we have some new science images. I'll show you a few of them. This is a lensing cluster. So I showed you some lensing effects. Actually, the cluster is this little knot down there. Okay, let's zoom in on it, and hopefully you again see those arcs there. Okay, so this is the kind of quality, again, you previously got from the Hubble Space Telescope. We're now getting from Euclid over a huge area of sky. If I go on to the next one, then again, this is just a star formation region. But again, huge view of everything that's in here. We can see all the detail that's going on. If we move on, then some interacting galaxies. And again, maybe it's so hard on here, but on my screen, you can see the stars extending and the stars crossing over between the galaxies here during this interaction. Another cluster, another galaxy. And if I can move on. Okay, so, too far. Okay, so Euclid, if I can go back, is going to make 20 observations every day. Okay, I'll just skip to the bottom there, because what we've seen is 10 observations. So what I've just showed you, Euclid will do in half a day in operations. And it's going to do it for 6 years every day. Okay, it is just awesome, right? It takes an observations every hour. In that observation, it has about 15 minutes taking the vis images you see. At the same time, it's doing the spectroscopy, and then it switches over and does the 3 colors in the remaining sort of 45 minutes. So this takes a whole hour. It does 20 observations for 20 hours, and then the remaining 4 hours are spent downloading all the data to the Earth. ESA has opened up a new channel for us because the data is way bigger than any other mission it's ever done before. Okay, so that will be a day's work for Euclid. It is a day's work for Euclid. Okay, but I said the aim is to try and make maps. So, you know, Euclid will look at a sky like this, and what we really want to do is probe behind what's there and see whether it really is the dark matter and the patterns we expect to see, and then probe those patterns in the gravitational lensing in the dark matter, probe them in the galaxies and see if they're matching our theories and our theories with the dark energy in them. Try and disentangle what's going on. As I said at the start, we really don't know. We don't know what's going on. Everyone's proposing crazy ideas, which is kind of nice, but we'd like to have some direction. We would like to have some indicator of what's going on. And we believe Euclid is the survey that will do that. I may have mentioned about the processing. The processing of all this, again, is a huge challenge. We'll process hundreds of terabytes, both of Euclid data, and we actually take all ground-based data as well and process that. Actually, this is the most challenging part of Euclid. That's where the other sort of 500 million went on, was being able to process this. Because we take all that data and then we process it into these maps, and then they're given to scientists and they'll be released again to the public. To do that processing, again, because it's Europe, things have to be distributed. We have 8 Euclid data centers across Europe, 1 in the USA. They churn away day and night processing this data. But the UK's is here in Edinburgh. Okay, the UK's one is being hosted, really, this is the Higgs Centre of Innovation at the Royal Observatory on Blackford Hill. It's hosted by the Institute for Astronomy in the Department of Physics and Astronomy. And we are processing that data now. Okay. So again, it's very exciting. We started full operations in the middle of February, so we've been going for a few months now. We had lots of kind of calibration, but this is how Euclid works. It's basically kind of a machine gun. It looks at a patch, then it moves on, looks at a patch, moves on, looks at a patch. It'll do that for 6 years, okay, but build up these maps of the whole sky. I think the exciting thing, again, is that even though we've only going for a few months, we are already the largest astronomical imaging survey in existence. We have surpassed everything that's gone, and we're about a third of our way into the first year of a 6-year mission. This startles even astronomers. Everyone says Euclid is just off the scale in everything, and so it's a big deal for what's happening with Euclid. Okay, I'll just close with some thoughts that, Euclid has a mission. Its mission is to try and understand and probe dark energy. The way it does that is essentially to make 3D maps of where all the galaxies and the dark matter is. And again, so we can do this pattern comparison. We compare those patterns that we see in the galaxies and the dark matter with what we're predicting for dark matter, but in particular for dark energy. Very small and subtle effects there. We're doing that, basically we're turning the universe into a laboratory. Okay, but the byproduct is we get to see the universe for the full time in high resolution. But its aim and its reason we got funded was because the questions we're asking are fundamental in terms of understanding perhaps the most mysterious things we have in physics, at least at the moment, which is dark energy and dark matter. But we have plenty of theories to try and compare with. So even the comparison with the theories is a huge computational challenge that we have to face still. So there's lots of excitement and lots of things still to do within Euclid. I show this. This is it from a Euclid consortium a few years ago. Euclid now has 2,370 scientists working on it. Okay, I have to say they're not working as hard as some of us, but it's a large consortium which basically everyone or nearly everyone in astronomy has signed up to be part of. 260 institutes and laboratories over 17 countries. So it's a huge effort, but I want to emphasize the role the UK has had. That we've been there from the start, we've helped design things, we've designed the concepts, we've designed the scientific goals. We're processing the data, we'll be doing the science as well. So I think we've got a lot to be proud in the UK. Okay, I'll stop there and take any questions. Thanks.
Thank you very much. Brilliant stuff, thank you. Good to see that Euclid's taking pictures of galaxy clusters just like ours in Spain. It's really good.
Absolutely. We should compare.
Yeah, that's right, we should. So we'll ask questions in the hall first. We've got a microphone here. If you could put your questions on Zoom. Will they be able to speak to us on Zoom tonight, Peter, or is there a problem with it? I'm not going to risk it. So if you could actually write your questions in Zoom and write them on YouTube as well, if you have any, then we'll ask them out. So any questions? No?
Yes, thanks. When you had the images of the Perseus cluster and the halos around the stars, what are we actually looking at there? You were saying it's dark energy, but
no. What I meant was
dark matter, rather.
Yeah, what I meant was that the interesting thing is, of course, we knew that the stars were concentrated in galaxies, but with these images, we're actually seeing that further away, we might have expected the matter to be falling off and the stars not to be. There are still stars there. And so the question is, one of the questions is just why are they still there further out? There must be something that's holding them. And at the moment, the only thing we can think of is that dark matter can have halos, little kind of collapsed structures, and they may be being bound by those. And those exist further out than where we were seeing the central concentration of the galaxies. So we're not seeing dark matter directly. It's just we're trying to explain why it is that the stars seem to be existing in places we thought they maybe shouldn't.
Okay, so the galaxies themselves are very much extended from what we
so
thought.
The galaxies themselves in dark matter have
it's not micro-lensing events from something behind it. It is the galaxy. Thank you.
Thanks. Great talk. One of the things that I was really interested in was your cold dark matter simulations of the filaments. And I'm curious as to whether you use the initial data from the microwave background in terms of amplitudes and two or multi-point stats
Yeah.
to seed your simulations?
Yeah, yeah. I mean, it's a good question, and one of the things, again, there's not time to cover everything, is one of the triumphs, I think, of our picture of the universe is it's not kind of, we've not had to produce a patchwork of theories where we go, okay, this is an explanation for the microwave background. Let's change everything. We'll have an explanation for galaxies and the distribution. It's the same theory linking everything. So you're right. When we run those simulations, the initial equations we set are basically the ones that we see in the cosmic microwave background. We have the amplitude of the variations. We see a variation in temperature, but we can translate that to a variation in the gravitational potential of dark matter. So we can use that and then run the simulations and just see what's it look like. And again, one of the triumphs is that over those 13 billion years, we can start at sort of 400,000 years, run the simulation for 13 billion, and end up something that looks very much like what we see in the universe today. Mm-hmm. So it's not just that we're explaining over kind of various scales, we're explaining over time in a very detailed way. That's the theory is very powerful in that sense.
Great. And it's, from memory, it's 1 part in 10 to the 5 or something
Yeah.
for the amplitude?
Yeah.
Perfect. Thanks.
Any other questions? Yeah.
Thank you. This is what about dark energy? You've talked a lot about the cold dark matter and its distribution, which is obviously non-uniform across the universe.
Sorry, I'm missing the...
You've talked a lot about the cold dark matter.
Yes.
And its distribution, which is obviously non-uniform, as you've described. In your computer modelling, do you assume a uniform distribution of dark energy?
Yes. So again, I guess what we're using at the moment are maybe the simplest things we can put in. Again, they're clearly exotic, and we need to understand more of them. As we said here, for the dark matter, we put initial conditions which are exactly what we see in the cosmic microwave background or inferred by them. For our simulations in terms of dark energy, at the moment, all we're putting in is Einstein's cosmological constant. Now it works, and it gives us answers that match the observations very well. But there are these kind of, these arguments about why we just don't think that's the final answer. It's not really explained what's happening with the vacuum energy. It's not explained why it has the value it has. So we're kind of unhappy with these explanations. Now, when we start trying to build other theories or other models, then it turns out there can be variations, okay? And these will affect things like how structure forms. So we are trying to see, in our other theories we're testing, it can vary spatially, and it can vary over time. And then hopefully we should see those effects on the patterns we're looking for. And so we can try and test those things.
Okay, thank you.
Anyone else here?
So Euclid's got a 6-year mission to complete its survey, but I guess at some point you're going to have a critical mass of data that's really going to make a difference in terms of saying what models fit well and what models don't. Mm-hmm. What's your anticipation of when you're going to start seeing the sort of wave of new evidence coming out of that?
It's a very good question. I mean, the 6 years comes from the fact that we need to collect this huge amount of data. And again, the reasoning, the logic is that these effects caused by dark energy are very small effects. But we don't have any other route in. So we've got to try and do this route. But they're small effects, so we need a large volume just to statistically measure those effects. So that once we've got that, the survey is almost completely designed for us. And the time scale of 6 years is just what fits it. But you're right, we have a number of data releases scheduled for which will be kind of like when we tell the world what we found. We're going to analyze the first year's worth of data. We started in February this year. We'll probably finish in February next year. That data will then be released to the consortium, so the consortium can do its science and do its testing of models. It has a year to do that, and then there's a worldwide release of everything. Our results, our data goes public based on the first year. Now, of course, that's only a sixth of the full data set. Okay, so it won't be as grand. However, we already know that almost no matter what we do, it's going to be orders of magnitude better than anything we've ever had before. So my feeling is that at that point, we could almost expect that if we're going to see anything major, we may have tantalizing hints at that point, right? It may not be true because it may just be it's so difficult. You know, we will struggle to analyze even the first year's data. So it may just be, you know, may not be the best results, but it's still going to be better than anything else. But I've argued that actually it's very important because we might see tantalizing things of things we'll have much bigger measurements for. So actually I think there's a lot of interest in what we get in the first year. The second data release is halfway through the mission. So that's actually 3 years worth of data. At that point, hopefully we've got everything right we got wrong in the first data release, because we're going to get some things wrong. Okay, so I think that's interesting because, again, we might be much more secure and happy. We've got more statistics from big volume. We've probably sorted out a lot of issues we may have had with the first year's data. So I think the second one will be important. Of course, the third one is just wrapping everything up, but statistically, that may not be as exciting. It's just maybe, as I said, just finally getting over the finish line. So I think the first, and so 2 years' time, middle of 26, and then halfway through the mission, 28 or something like that, 29, is probably going to be interesting things. We intend to have worldwide press releases of what we're finding, so hopefully you should hear about it.
Thanks very much for an excellent talk, Andy. I just wanted to ask, with this massive data coming from Euclid, what sort of impact do you see it having on the development of AI?
Again, another good question. I mean, it's interesting because space missions just take such a long time to do. I was a young man when I started this, and it's just taken, I mean, we started conceptualizing it 20 years ago, and then what we just wanted to do was build the biggest and the best that we could. We actually couldn't conceive of anything better, but also we realized that what we were building is optimal for dark energy. Okay, you could build a survey that goes slightly deeper or something, but actually the signal for dark energy we think is more kind of in time close to us. So if we build something bigger, we're looking back to maybe where there's less signal for the dark energy to be detected. So we've built what we think is an optimal dark energy model. Sorry, I've forgotten what your question was. Of AI, yeah. So as I said, because of that timescale, a lot of the methodology we put in place had to be developed or started development 10 years ago. It takes 10 years just to build these things. And even the computer processing, we had to think what we wanted to do 10 years ago and then make sure it happened. In a sense, that's been a success. We've got a data analysis which is working, and we're now fine-tuning it to get the answers. But you're right, in the meantime, things like AI have come along. So what I think is going to happen is that, again, for the first data analysis, we'll use kind of the tried and tested methods that we have. But beyond that, I'm sure much better algorithms will come along, probably based on artificial intelligence and machine learning. And that'll boost us even further, become easier to do this. And we can start exploring more models, putting more things, more tests. So I think there's kind of a big, there'll be a big development over the course of Euclid, just starting to harness those things and then making my guess is that by the time you finish Euclid, you'll be able to download it and do it on your laptop, right? Because we'll have such impressive methods, but they're still to come. They're still in development.
Okay, I think we should probably end it there. So can we thank Andy again? Thank you very much.
Great, thanks. Oh. I'll leave that for you.
Good.
Cheers.
Of universe-spanning importance, and you didn't have to pay £200 a ticket for it either. So.
Cheers.
The sky in June 2024. That is another of our deep field images of galaxies. That's the exclamation mark galaxy. So hopefully Euclid can capture that one as well. That'll be interesting. As always, thanks to, that's Pat Devine's version of that one. He's the one who asked us to photograph that. Thanks to Alan Pickup for his monthly sky notes as always. So we always tend to base it on that. So what do we see in the sky in June? Well, it is twilight all night long, so one of the things we can look at is noctilucent clouds, and that was a nice image from John Briggs last year. And these are very beautiful night shining clouds based on ice crystals. It needs water vapor and dust, which may be dust from meteors or whatever, and very low temperatures to form. And they are at a height of about 80 kilometers, and that means they're still in sunlight even when all the normal clouds that we see are out of the sunlight and go grey. And you can see them from about an hour after sunset to about an hour before sunrise. There's always a question earlier on in the year, is this actually a noctilucent cloud? And if you're having to question it, the answer is probably no, because as soon as you see them, they're sort of really ethereal, beautiful clouds, and you know as soon as you've seen it that it is actually a noctilucent cloud. Denis Buczynski, I believe, saw it from up north of Inverness, one of my members, recently. I think that's the first we've heard of. So they are around now, so keep an eye to the north after sunset. Yes, we are in the twilight zone again, which is why it's not so great for astronomy from Edinburgh. We've passed through the astronomical darkness and the civil nautical twilight, and we're really sort of civil twilight really now, so we don't get any real dark here at all. This is a chart from Dominic Ford's In the Sky. So that's really what's happening here, why it's not great for astronomy. But the moon is still around, or it's new at the moment. And you can image that in bright skies. You can image it in the daylight, so you can observe it in the daylight, as a number of us have been doing recently. And if you have an infrared pass filter, which are very cheap to buy on your camera, then it really does look like you're imaging it in the dark night sky. So those are the dates for the different phases, but we are just about just after new at the moment. We do have our moon project, which is just up and running now. We've got a WhatsApp group for that and information on our members' website. These are the objects that we've chosen to look at initially, some of the major features that we all know very well. And what we're hoping to do is capture them either with our telescopes in Spain or with our own telescopes here, try and capture them at different illuminations, see how they change, look at the shadows and things like that. So we've got quite a lot of interest in that project, and if you want to be part of it or just come along for the ride, as it were, then sign up for that project. Planets in June also not particularly great. You'll have heard in the press about all these amazing alignments of planets, which, well, they sort of do align, but they always align, but you're not going to see anything very amazing in the sky at all, so go to bed, don't stay up looking for it. Saturn is pretty low in the morning twilight, about magnitude 1.1, but it is very low, so you're not going to see very much. You might catch it with your eye or with a pair of binoculars, but don't really bother with it telescopically. Similarly, Mars is also very low in the morning twilight. Not a great time of year for planets at the moment, so don't waste your time on that. And that's showing the orbits where we are at the moment, which is why you can see why we're not seeing them. Mercury and Venus are behind the Sun. Mars is just out to the side, and Jupiter is as well a little bit, and Saturn is, but not particularly well placed for us, not opposite the Sun anyway. Sadly, meteors, this really isn't a very good month for astronomy at all, is it? There's nothing much in the meteor calendar around about June. We know in August we get the Perseids, and that's always worth looking at. But in June, there's really nothing very much at all. This is data from the Global Meteor Network. They also have this dial on their website, which is a sort of meteor shower flux, what you can expect. And we are sort of down to background levels. You might expect 25 meteors an hour under a dark sky, but nothing worth speaking about. However, on our website, as you know, we have 15 meteor cameras from members in our society now. And we have a lot in Scotland, but we also have some in Europe as well, in Slovakia and Germany. So look at the different camera feeds there, and you'll always find something. This is from 2 nights ago from one of Radim's cameras in Slovakia. And that's the coverage we now have. We have taken over Scotland totally. We have taken over the north of England, got a bit of Germany and the Netherlands, and Radim has really taken over Central Eastern Europe totally, as you can see with his full cameras. So well done, Radim. Comets, we're a little bit better off comets. Ponsbrook's, 12P Ponsbrook's has gone now, but it was a really good object, a very impressive comet. That's still one of the last images one of our members took, Robert Arnold, on Sky, and it's been a really good one to follow. And we followed that for quite a while. That's the light curve from all the observations that we had in our society, and we followed it from pretty much August last year, I think, until we lost it from our skies in March or April. But it was really a nice one to see that one. The other one that we're doing a lot of following with a telescope in Spain is 29P Schwarzmann-Wachmann 1, which is nothing like so impressive. That's pretty much all you ever see of it, a fuzzy blob with a brighter nucleus. But it is a very interesting comet, as we've spoken about before in the newsletters, and Douglas has mentioned a few times. It has many outbursts from its surface and the nucleus, and it's about 60 kilometers across. It has now almost gone from our skies. It is low in the west, so a lot of UK observers are not going to really be able to see it, but we're still able to track it from our telescope in Spain. And this shows in the 23-24 apparition of the comet, all the different outbursts that it has. Because it has an orbit which is almost planetary, it comes around every so often, so we can monitor it for a long period of every year. So that's why it's really interesting. And our telescope in Spain did actually discover one of the major outbursts, in fact, the major outburst of this apparition, and we caught it about 2 minutes before the outburst actually started, so we had really good data from the very start of it all the way to the peak and to the trailing off. So beginner's luck, I think you would say, for that one. This is the one we're holding out a lot of hope for, 2023 Chushinshan Atlas, and we're calling that our centenary comet. We've decided it's our comet because come October, when we have our 100th birthday celebration, it could be and should be naked eye visible. Nick James of the British Astronomical Association is starting to sound positively happy about it. He's often very, very wary, saying they can just fizzle out and become damp squibs, as they often do, but he's actually starting to sound positive about this. So yeah, it could be a good one. It's currently fading. I don't know if you can see that you can. That's the line we would have expected it to follow, but over the last few weeks, the data points, many of which are ours, have started to go off, but that's to do with the Sun-Comet observer angle, phase angle as it's called. It's not actually necessarily a fade in the brightness of the comet itself, it's just observational. And it does have a nice tail as well, sorry. This chart is from COBS, where most amateurs send their cometary data, and you see that is the line that is expected to follow, and it should be naked eye visible sometime in October, we hope, if everything goes to plan, unless the sun eats it up. And that is one of the latest images we've taken. The tail is around about getting on for a third of a degree now. The moon is half a degree, so full moon's half a degree, so a third of a degree is quite a long tail. It's about magnitude 10, so it's still not very bright, but it's telescopically, with imaging really, it's proving to be a very, very nice object to follow. The sun is obviously in the sky in the summer. Well, that's not true in Scotland, obviously, but it's up there. If you're observing it, obviously do it safely. If you don't know how to do it safely, don't do it, but ask us because we can help you to do it. It's not difficult to do if you know what you're doing, but it is so dangerous if you get it wrong. This is what it would look like in white light. This is a recent image from Robert again in Sky. Some nice sunspots there, a lot of detail. And this is the same sort of view in hydrogen alpha, and there's a nice filament showing up there that we've been seeing over the last few weeks, last week or so. Robert Parsons, one of our new members, also captured the filament in some very nice prominence loops as well. And Robert also caught this, which this is actually a sunspot group, but in hydrogen alpha. It's called AR3697, active region, but this is the second time it's been around the sun. The first time it was around It's called 3664, which is the one that actually produced the coronal mass ejection that caused those amazing auroras that we had. So that's what it looks like in hydrogen alpha. So it's always a bit tricky saying what you can see in the sky in Edinburgh in summer. So I'll point at some of the brighter things. Alan mentioned last month about the keystone of Hercules. It's high up in the south. This is round about midnight BST in the middle of the month. And as we've shown, just exactly the same sort of view as Euclid had for its globular cluster. We have our telescope in Spain. That was pretty much first light for our wide field telescope in Spain, M13 globular cluster in Hercules. We always talk about the summer triangle, which is starting to get higher in the sky. 3 bright stars, Vega, Deneb, and Altair. That's always a good signpost and will be high up in the sky for most of the summer and beyond that into autumn as well. There are a few constellations that we never really get to see much of in Scotland during the summer, Ophiuchus, Scutum, and Sagittarius and so on, because they're just really too low down. So there's quite a few interesting things in there, but we never get to see it. So this year we're going to cheat. So we can feel smug about it this year. So for the first time, we don't stop this sort of astronomy because we have our telescope in Spain. And as you can see, it's got astronomical darkness all night, even all year long, even in the middle of summer. So if you look at the ephemeris with the sun in the middle of June, 21st of June, we actually get more than 4 hours of true astronomical darkness. And if you take nautical twilight as effective darkness, then we get 5.5, 6 hours of darkness. So we can carry on. It means Ian and I don't get any sleep over the summer, but keep running the stuff. But it's there. So that's why we set up our telescope in Spain. So I think we can feel smug about that we can actually carry on doing astronomy. Forget the Scottish weather, although the Spanish weather is pretty bad at the moment. So what can you see in Travinca? I'm not going to go into too much detail, but one of the things that we rarely see here, I try to find it most years, is Antares in Scorpius, a red supergiant star, which is always really low down here, but it's a bit higher up in Spain, and it's interesting because it illuminates the Haro-Ophiuchi cloud complex. And I've said to Ian, I think this would be a really nice project for our wide field scope to make a mosaic of that region, because it's quite a wide region, but really very impressive if you look at pictures of that. It's still pretty low down, but if we can get an hour or so every night it's clear, then we should build up a nice mosaic of that pretty quickly. So hopefully by the end of the summer we can show you what we've got, and obviously we want everyone to be involved in processing that data as well. You'll all have access to that. Yeah, that's the area. Antares is often down there. It's pretty low for us, and it means rival to Aries or rival to Mars because it is so red and often mistaken for Mars, or has been in the past. The Very Large Telescope has actually produced this image. I wouldn't say taken this image because it's used interferometry, but it's put that together from the data of Antares. So Ophiuchus, as my son said when he saw that, it's just some old guy carrying a snake, isn't it? I said, yes, it is. So it's Ophiuchus, the serpent bearer with its head and tail and so on. If you've been reading the newsletters, then you know that we've done a little bit of stuff with Barnard's star recently. We set up a project last year when we first set up our telescope to see if we could detect the proper motion of Barnard's star, because it has the largest proper motion of any star. We all think of the stars as not moving very much, and the constellations are fixed, which is mostly true, but they do all move a little bit. And Barnard's star moves quite a bit. It's pretty faint, a red dwarf. So we took some images of it last year, and 8 months later, this year, we've taken some more images of it. And yeah, lo and behold, even with our wide field scope, Barnard's star does actually move within 8 months. So all you C-star owners, see if you can do it as well. I don't see why you shouldn't. We've got lots of C-star users. That would be a good scientific experiment for you to show proper motion. These are the constellations I mentioned before that are full of interesting objects that we never get to see. but with our telescopes in Spain, we have, this is from last year, the Eagle Nebula. Euros processed that from our data. I think that was the wide field scope it had to be. Literally this week, we've got some really nice data on the Trifid Nebula, and that's Pat's process of that. And this was from last year again, the Wild Duck cluster, embedded in an amazingly dense cloud of stars and dust as well. So I think these are the sort of images that impressed us with the skies down in Spain. So lots of interesting things we can still do over the summer. You all have access to the data. You can all put in your requests for objects. So have a look on your planetarium programs, what you'd quite like to image, any projects you'd like to run. You know how to put the requests into us. It'll come through to Ian, he'll schedule it. Let's carry on doing astronomy throughout the summer. And that's the end of that.